Okay, so this will be uploaded to YouTube for you to watch later. Okay, has anyone watched the videos from section 1.7 or 1.8 yet? No, you didn't. You weren't supposed to, but just in case you had gone ahead and watched them. 1.7, 1.8 are what we're going to talk about today. So if you didn't turn in your photoelectron spectroscopy, did you all get your photoelectron spectroscopy photo turned in?
I didn't.
If you did, then that's great. If you didn't, then get it turned in. I did make an announcement as well as I altered the assignment on Canvas. There were a few questions that you needed a formula for that for some reason the POGO didn't provide, and so I provided that for you in an announcement. Yeah, it was weird. I don't know why they didn't provide it in there. When I went through it before assigning it to you, I was like, oh yeah, it's like oh, it's there. I just assumed that they would be smart and include the formula, but they didn't. Yeah, that you're asking about. Anyway, so the formula was the energy of a photon based on its frequency, or the frequency of its no, not its frequency, its wavelength. Frequency and wavelength. Anyway, they're all connected. So let me pull up good old P table. Okay. So if you're following along at home, pull this up. If you're following along in class, you can pull this up on your computers. Okay. So the first thing that we need to talk about is atomic radius. Okay, so what is atomic radius? It's pretty simple. Elijah, Jeanette, Ben, Christian, Jane, Quinn. What is an atomic radius? The distance away from the electron. Okay, that's an interesting way to put it. I get what you're saying, but Quinn? Yes. So the distance between the nucleus and the outermost valence electrons. So it really is just the size of the atom. Okay, all of you are trying to make it more complex than it actually is. It is just the size of the atom. Okay, so atomic radius. As we look at this here, there are certain trends on the periodic table. The atomic radius increases as you move down the periodic table. This probably makes sense. Why would the atomic radius increase as you move down the periodic table? Quinn. You have more electrons, you also have more of everything, right? You have more protons, you have more neutrons. So it's just things take up space, so it's bigger, okay? So the atomic radius is bigger as you move down the periodic table. As you move right on the periodic table, would the atomic radius go up or down as you move right, from left to right?
It would go up.
You think the atomic radius would go up as well? From left to right. Why would that happen, Christian? So the numbers are going up. So for instance, potassium has more, or it has less stuff than bromine, or bromine, however you want to pronounce it. Okay, potassium only has 19 protons. Bromine has 35 and equal numbers of protons as electrons, right? So it would make sense that it gets bigger, but it's not, okay? The atomic radius actually goes down as you move right on the periodic table. The reason for this is because the number of protons is increasing while it is true that the number of electrons is increasing, but if you're in the same row here, so we have columns and rows, right? If you're in the same row, so let's take manganese, okay? Manganese and gallium as an example, right? Manganese has fewer or more valence electrons than gallium. Fewer or more valence electrons. Manganese to gallium.
We'd have fewer, right?
Yeah, manganese has fewer valence electrons. Okay, and and gallium has more, but because of remember with Coulomb's law, right? Because of Coulomb's law, the electrons in gallium are being pulled toward the nucleus more than in manganese, in the valence shell. Okay, so gallium has a smaller radius than periodic table atomic radius. So if we look at this here, okay, if we look at, oh, really? You know, okay, here we go. I mean, that kind of works. Can you give me numbers? This is better. Okay, so do you see that potassium is smaller than bromine? Do you see that? They are in the same row, and therefore they have the same number of shells, right? They have the same number of shells. When you add another shell, so when you go down a row, when you add a shell, it kind of resets. Okay, does that make sense? And this is why the periodic table has the columns and rows that it does. Okay, this is why the periodic table has the columns and rows that it does. So strontium has a larger atomic radius than iodine. Okay, beryllium has a larger atomic radius than fluorine, because the atomic nucleus is pulling in on the electrons more strongly in that outer valence shell. Okay? Questions on atomic radius and what that has to do with everything? Yeah.
So other than figuring out how this radius.
So the atomic radius is relevant in a pretty limited number of things. When you're trying to figure out like the interactions between atoms in a molecule, then you might use the atomic radius, but not all that much.
I have a question.
But I think that it is important to understand.
Yeah.
But I'm not exactly sure. You would probably only need it when you're talking about really like complex, in detail, interatomic reactions. Elijah, you had a question?
Yeah, so how do you measure atomic radius?
So atomic radius is measured in picometers. That's a great question. It's measured in picometers. Yeah. So you look at this here. Sometimes they call it a covalent radius.
Yeah.
But yeah, you can see here it's measured in PMs, picometers. So calcium has an atomic radius of 17.4 picometers, while bromine has an atomic radius of 1.14 picometers. Okay?
Okay.
The smallest is helium. Helium has the smallest atomic radius at 0.93 picometers.
Because it only has one.
Wait, Oh, it says oxygen. Someone lied to me. Someone has lied to me. It appears that fluorine actually has the smallest weight.
Why would that be? Because helium only has one proton, so it should be the smallest,
This
right?
is wrong. This is a different thing. This is a different thing. I guess the covalent radii is similar, but not the same thing as atomic radius. Let's see here. Yeah, that's better.
Wait, so what were you looking at before?
That was covalent radius. They're
Oh,
similar, but I guess they're just slightly different because helium is, yes, this is correct. 31 picometers. This is the way that we were looking at something that was giving us different information, similar, related information, but not the same. Okay? So helium is the smallest, and that will help you.
Oh, there you are. You want a orange Julius?
no, I don't want anything.
I want orange Julius. Did you bring it up for the class, Elijah?
Mom, I'm in class.
What? Under what circumstances would a teacher quarantine? If I tested positive, or if someone in my family tested positive. One of my students, I don't touch you because you're disgusting meat bags full of filth. Okay, so let's get started. Moving on after atomic radius. Is there anything else that you wanted to talk about there? So atomic radius, and Quinn, you already anticipated this. Atomic radius is connected to ionization energy, right? So remember that the ionization energy is connected to Coulomb's law, right? So if we go back to our periodic table, ionization energy increases as we move right and decreases as we move down. Ionization energy is essentially the opposite of atomic radius. Okay, because the more the electrons are pulled in on the nucleus, the higher the energy. So this means that as we move right, the ionization goes up, and as we move down, the ionization energy goes down. Okay? So if we look at the periodic table in terms of the trends of ionization energy, then we get something that looks like, oh, wow, that has all of them. Ionization energy, so does this make sense? So increases that way, increases that way. Yep.
So this happens because there's more protons and neutrons as you go right, but it's on the same layer, right?
Yes. So if all things being equal between the rows of the periodic table, as you move right, the nucleus pulls in more strongly on the electrons, thus making it harder for the electrons to escape. And what do we mean by harder is requiring more energy. Okay? So ionization energy increases going up and to the right. Yes, up and to the right. Okay? Ionization energy. Yes, Christian.
How much energy would you need to knock out the electron in helium?
Helium is very difficult because its atomic radius is so small. Its ionization energy is very high. And I think that it takes something like 300 something kilojoules. No, more than that. It's like 2,000 kilojoules per mole. Is it more what? More energy than what? The sun? No, no. No, the sun has no problem ionizing helium. In fact, that's exactly what the core of the sun is ionized hydrogen and helium.
But how could it ionize it next to the
Hey, Elijah, you should mute yourself for a second.
Oh, sorry.
It's a very loud car driving by. What were you saying, Quinn?
So when you ionize something, you have to have it in the vacuum chamber so that the electrons will be well, the particles going to collide, and then it's like not anymore.
Yes.
How can you do that in a natural environment? How
It-
is the sun able to
The amount of energy, the amount of heat in the core. So when you ionize something here on Earth, you're not able to keep it ionized for very long because it interacts with other molecules, right? In the sun, it has so much energy that everything just is ripped apart. That's what plasma is. A plasma is everything's ionized. It's naked protons and naked electrons flying around. That's what a fusion plasma is. Okay. Yeah. And the sun has a crap ton of ionized helium in its core because it's been fusing hydrogen for 5 billion years. Okay. All right. So the next trend that we need to talk about, which is another related thing. I know it seems like we're talking about like the same thing, but they're all different. And this is a big one. And it is electronegativity. Okay, electronegativity. Follows the same trend, or let me rephrase that, a related trend. Okay? Ionization energy goes up as you go right and up as you go up, right? Electronegativity is the same way. It is the same trend line, okay? So electronegativity is highest in fluorine, okay? So the difference between ionization energy and electronegativity is just kind of a basic one, but electronegativity, you could define it as the amount that an element wants electrons. Okay? The amount that an element wants electrons. And it is highest in fluorine. Why not highest in helium? Why isn't it highest in helium? Any ideas? Why is electronegativity not the highest here at helium? It's the amount that an element wants an electron, yes.
Okay, so what was your question again?
Why is it fluorine that has the highest electronegativity and not helium?
Because the noble gas is dominated.
Yes, because helium is a noble gas. Helium is a noble gas and therefore has all of the electrons that it wants. Okay? Helium is a noble gas and therefore has all the electrons that it wants. This is also connected to the reason why the ionization energy for the noble gases is so ridiculously high. The noble gases have insanely high ionization energy because they are very happy where they are. And they do not want to gain or lose an electron in any way. So also why they don't interact with other elements. Okay? Questions on that? Okay. So electronegativity, so we can go here. Look at electronegativity. So krypton and xenon have some electronegativity, which is fascinating. Why does krypton have electronegativity? I do not understand that. Somebody's got to explain that to me sometime because I don't get that. That doesn't make any sense. Google. Fluorine, however, look at the electronegativity of fluorine, 3.98. That's pretty crazy. That is pretty crazy. It is, and then here we have the lowest electronegativities. The lowest electronegativity is francium.
Oh, okay, so they're able to form krypton and xenon are able to form bonds with fluorine to make molecules.
With fluorine?
Yeah.
So krypton and fluorine react? What? I didn't know that. That seems really dangerous. Fluorine is like super dangerous by itself, and krypton is also very dangerous by itself.
Yeah, you're super big.
Well, oh gosh, that's kryptonite. Okay,
You know, it's the same thing.
it is not the same thing. Krypton. So
You point to the map.
actually, you can actually breathe in krypton. You can breathe in xenon as well. They don't like to react with stuff, but with fluorine, krypton is dangerous by itself in that if you breathe it in, it likes to just sit in your lungs and it can displace oxygen. So it can be dangerous. Anyway, can we try it out? No, but there's a great video by a guy that lives here in Utah that he says, so he used to be a chemistry teacher and now he's just a full-time YouTuber because, well, why not? I'm not going to show you the video. We don't have enough time. He breathes in all of the noble gases. And so not at the same time, but so he does helium and then neon. Helium makes your voice all high, right?
Yeah, and then,
Because the density is really low.
the one that makes your voice deeper is, I think it's that, isn't it?
Hexafluoride.
I actually saw that video.
Yeah.
He only goes up to xenon because the
Yeah,
other two are really dangerous.
you can't get radon because radon is super radioactive. And yeah, anyway. But xenon is really heavy and just sits in your lungs, but it sounds crazy. Like it makes his voice super low because the density and the weight is higher than air. Anyway, so that's electronegativity, okay? Francium wants to give away its valence electron so bad, okay? It just wants to be gone. And fluorine really wants an extra electron. Okay, that's electronegativity. Questions on electronegativity? No. Okay, final thing that we need to talk about, electron affinity. Okay. Electron affinity is the, well, it's how much the, oh wait, so I wanted,
Is that like because of that getting another electron?
so electron affinity is, yeah, it's the ability of an atom in a molecule, oh, sorry. It's the ability of an atom it's like it's the, how do I say this? It's it's how much energy is released or gained when an atom is ionized. Okay, so if it can gain energy or lose energy, and so for instance, metals want to lose electrons because the nucleus doesn't pull in very strong, and the what?
It says the electron affinity of an atom molecule is the amount of energy released when an electron is attached to a neutral atom or molecule in the gaseous state forming a atom.
That sounds like way too many words. It's the energy of gaining or losing an electron.
Okay, yeah.
Okay, so for the metals, these guys, right? It is easier to lose electrons and for non-metals, it's easier to gain electrons. Okay, so electron affinity, and you can see a little bit of a trend. The electron affinity is higher over here, which makes sense. And it's the energy, yeah, it's the energy of gaining an electron over here or losing an electron over here. And if you go to P table, you'll see that the electron affinity is generally positive. There are some negatives or some zeros. Okay. Cool. Cool. Last thing that I wanted to talk about with electronegativity that I forgot to mention. Electronegativity is the amount that an atom wants an electron, right? But it isn't just by itself. Oftentimes the electronegativity means that when it is bonded to something, it pulls on the electron more. Okay? So if we look at something that is bonded with, so let's look at like sodium fluoride. Okay? Sodium fluoride, molecular model, molecular structure. What? So here it is. This is what I wanted right here. So if we look at this image here, good old Shutterstock, we can see this here is the sodium. This here is the fluorine. Okay? The electrons are going to hang out almost always. The shared electron that they are sharing between them is almost always going to be by the fluorine. Okay? It's going to hang out over here because the fluorine has such a high electronegativity that it will stay here. This impacts polarity. Okay? This is a polar molecule because the electron always hangs out on this side. The shared electron always hangs out on this side, thus making this side of the molecule negative, and this side of the molecule will be positive. Okay? Thumbs up? Yeah. No. Okay, so those are the periodic trends. Okay, any questions on periodic trends? So we have atomic radius, we have ionization energy, we have electronegativity, and we have electron affinity. Cool? Sick, dude. My goodness. Okay. Jeanette, did you have a question? You're good? Okay. Let's move on.
I'm good.
Perfect. What? Quinn is saying hello to the Zoom people. So, all
Hi,
right.
Quinn.
Quinn says hey. Hey. All right. Let's do the final topic that is in this unit is the valence electrons and ionic compounds. We're going to get to that in just a second, but I want to now run a couple of practice problems with our friend Mrs. Pooty from the AP daily videos. I'm going to attempt to share the audio from this video with you all. Hopefully.
Hi,
this will work.
friends. I told you September 26th.
Okay, so let's see if this works.
This video is on topic 1.7 periodic trends, and today we're going to take a look at some practice questions on periodic trends from the AP exam.
How can I help you, Ms. Roberts? Okay.
I'm Ms.
My
Roberts.
name is Alice Pooty, and I'm happy to be back with you on AP Daily. In the last video, we looked at different trends of the periodic table and reviewed why those trends occur. And so now we're going to take a look at some example questions. So for the first question, it asks, which element has the smallest atomic radius, nitrogen, oxygen, or sulfur? And you can see that on the periodic table, I outlined them in purple. If you remember from earlier, the radius decreases as we go across, which means that oxygen is going to be smaller than nitrogen and increases as we go down. So that means sulfur is going to be larger than oxygen. And so for the correct answer in this case, it's going to be oxygen, which will be the smallest element. The next question is, which element has the largest ionization energy, beryllium or magnesium? So this time they are outlined in orange. And for ionization energy, this decreases as we go down the periodic table, which means that beryllium has to have the largest ionization energy. And this is due to the fact that beryllium is a smaller atom, and so it is harder to remove those electrons. And for the last one, if we take a look at the electron affinity for germanium and selenium. And so the question is, which of them has the highest electron affinity? In other words, which one is the most negative? And so again, the trend going across the periodic table is that electron affinity increases. And so this case, selenium should have the highest electron affinity. And that's because selenium has more protons, which means that the electrons will be more attracted, and therefore the atom will release more energy when you add that electron. All right, let's take a look at some practice questions for you to work on. So this particular question says, in terms of atomic structure, explain why the atomic radius of gallium is smaller than that of calcium. And so I've outlined these in blue this time. And so when you answer a question like this, you want to explain your answer in terms of atomic structure. On the AP test, we often see students will talk about their location on the periodic table rather than focusing in on the atomic structure. So thinking back to what we talked about in the last video, please press stop, answer the question, and then press play when you're ready to continue.
Okay. In terms of atomic structure, explain, hey, Elijah, can you hear me? Okay, good. In terms of atomic structure, explain why atomic radius of gallium is smaller than calcium. So the question is not, tell me the trend, right? Don't say, oh, gallium has a smaller atomic radius than calcium because it's more right on the periodic table. No. You want to explain it based on the atomic structure. So Quinn, how would you explain it?
So since calcium is going to be like to have, since calcium is going to have more valence electrons.
Nope.
No, they're the same. Since calcium.
Nope. They don't have the same number of valence electrons. And they
Does calcium have one more valence shell?
nope, calcium and gallium have the same valence shell. Because they're in the same row.
Is it because there's more electrons and protons in calcium than there are?
What do you think, Jane?
Since gallium has more electrons in its outer shell, they're like connected, like bonded, pulled in by
So,
the nucleus.
okay, you're getting there. So you say that since it has more electrons in its outer shell, they're pulled in more by the nucleus?
Yeah.
Okay, you're so close. Christian.
I would say it's basically the same thing as the more electron has the type.
It's no, it's okay. You're all getting so close. It's the number of protons in the nucleus is higher for gallium. Thus, it pulls on the valence shell harder. Okay? Because gallium and calcium have the same valence shell. It's not about the number of electrons in the valence shell, it's about which shell it is. They have the same valence shell because they're in the same row. So the rows indicate the valence shell. Okay? If they're in the same row, they have the same valence shell. But because gallium has more protons in its nucleus, it pulls on that same valence shell harder. Does that make sense? Okay. So calcium has a higher, has a larger radius because it has fewer protons, and gallium has a smaller radius because it has more protons, and they have the same valence shell. Are we clear on that? Okay. Okay. Questions on any of that? Good. And there's going to be some reading that I'm going to assign today that has to do with this. Okay, that has to do with the shells and the periodic trends, and it goes into greater detail on this. Okay, so we're going to carry on with Mrs. Pooty here. Oh, maybe.
For this particular question then, I've addressed the atomic structure in two ways. So the first thing that I've mentioned is the fact that gallium and calcium both have 4 occupied energy levels since they're in the 4th row of the periodic table. and that gallium has more protons, 31, compared to calcium's 20. So just saying that doesn't answer the question. You then need to tie that back to why is it that gallium is smaller than calcium. And so since the valence electrons in gallium are more attracted to the nucleus, the atom is going to be smaller. So the second question then says the student claims the first ionization of energy of F is greater than that of Br. Do you agree? Explain why or why not in terms of atomic structure and Coulomb's law.
Okay. The student claims that the first ionization energy for F is greater than that of Br. Okay, fluorine is greater than bromine. Do you agree? Explain why or why not in terms of atomic structure and Coulomb's law. You agree. Why do you agree, Christian? Ben? Yes. Valence electron for F is closer to the nucleus than for Br, right? Okay, well, thanks for telling me where the location is. What does that mean? Yes. So this is a kind of question that you might see on the AP exam. Okay? And you will need to say, Coulomb's law states this, right? The distance between, as the distance between the particles increases, the attraction decreases by the square, right? It is an inverse square law. So you're going to need to say, Coulomb's law says that the distance increasing means that the energy or the pull between them, the attraction between them goes down by the square, right? Establish that and then say, fluorine has a smaller atomic radius. Therefore, the energy to pull the electron away, the ionization energy, is higher because of that distance. Does that make sense? So when it says, explain why or why not in terms of atomic structure and Coulomb's law, you need to say both of those things. You need to show that you understand Coulomb's law. You need to show that you understand Coulomb's law, and then you need to show that you understand atomic structure, and then you need to pull them together and say, I agree with the student because Coulomb's law says this, and atomic structure can be applied to Coulomb's law like that. Boom. Okay? The AP people are very persnickety about this kind of stuff. And that is not a word that I thought I was going to use today. They're very persnickety about this kind of stuff. You want to make sure that you show them that you understand the question, and then you answer the question exactly how they want you to. Okay? So when it says, explain in terms of blank and blank, you need to say, here's the first blank, here's the second blank, I understand them both, and this is how they're related to answer this question. Cool? Okay, moving on. Let's see what.
So for this question, like many of the other questions that we've done, this requires you to answer two things. So you want to answer the question of yes or no, do you agree? And then you need to explain why you do agree or not. But you also need to explain in terms of two things, which are atomic structure and Coulomb's law. So please press stop, answer the question, and then press play when you're ready to continue. Hopefully you said that you agreed. And the reason that you're agreeing to this statement is because according to Coulomb's law, the force of attraction is inversely proportional to the distance between the charged particles. And for fluorine, the protons and electrons are closer and therefore have a larger attraction and are going to have then a larger ionization energy compared to bromine. This is the end of the video. Thank you for watching.
Cool?
Cool.
Cool. What time does this class end again?
12:25.
12:50. It is currently 12:29, James. No. Let's now watch the 1.8 daily video as an intro to valence electrons and ionic compounds, and then we will discuss it as a class. Okay? Totally.
This video is on topic 1.8, valence electrons and ionic compounds. Today we're going to review how to determine the number of valence electrons and charges of elements using your periodic table. My name is Alice Pooty, and I'm happy to be back with you on AP Daily. Valence electrons, also known as outer shell electrons, are the S and P electrons in the highest energy level. On your periodic table from your first year chemistry class, you probably already wrote these numbers that I have on my periodic table to indicate the number of valence electrons. So for group 1, which are our alkali metals, there's 1 valence electron. For group 2, there are 2 valence electrons. Notice that we don't have anything written above our transition metals. Then above boron, 3 valence electrons, and then continuing across to 8 valence electrons that we have here. Valence electrons are important because their interactions determine whether elements will bond or not. And knowing the number of valence electrons allows us to predict what's the formula for our elements when they bond. This is also going to be a necessary concept for your Lewis dot structures, which is topic 2.5. Regarding ion charges now, again, you probably have these notations on your periodic table from first year chemistry, where our group 1 elements have a charge of +1. Group 2 is, 1 plus. Group 2 is 2 plus. We again skip the charges for our transition metals. Above boron, we have 3 plus. Notice there's nothing that's written above carbon, and that's because carbon generally doesn't donate or gain electrons. And then above nitrogen, 3 minus, above oxygen, 2 minus, above fluorine, 1 minus, and then, though it's a little bit hard to tell because my face is here, there's actually nothing written above helium. And again, that's because noble gases will not gain or lose electrons. And so as I mentioned before, if we know the valence electrons or the charges, then we can make predictions about what their formulas are going to be. So for example, let's say I have magnesium and calcium, and we want them to bond with oxygen. If I know what the formula is for magnesium and oxygen, I can also make predictions about what it will be for calcium and oxygen too. All right, so let's take a look at some practice questions for these. For the first question, you are given the electron configuration for an unknown element X and asked to write the formula for this particular compound and chlorine. And so in order to answer this question, what you first have to do is take a look at the electron configuration and determine what would be the charge of an element that would end in 3p1. So what I'd like you to do is stop the video, answer the question, and then press play when you're ready to continue.
Okay. Are we all familiar with electron configuration?
You went over it briefly.
Okay. Does anyone feel comfortable with electron configuration? Yes. Ben, could you give us a review of electron configuration?
The valence of electrons like one shell, but like different. So it's like how it's like S would be different from based on how the electron is.
Okay. Yeah. So these here, 1s and 2s and 2p and 3s and 3p, are the shells. Okay, they're the shells. And this here, this number, the superscript, is the number of electrons in that shell. Okay? So let's see what Alice does here. And she's gonna come back.
For this particular element, since it ends in 3p1, it would end up then having a charge of 3+. You probably even figured out that aluminum is the element, but if you didn't, that's fine because it doesn't ask you to do that. And since we're putting aluminum together with chloride, chloride ends in what, or has a charge of 1-. You're going to need 3 chlorides in order to bond with 1 aluminum for the overall charge to equal 0. And that means that the formula for this is going to be XCl3, or you could have written the formula AlCl3, and that would be fine too.
Okay. You don't understand how this works?
Okay, so it's giving you the electron configuration of X,
Uh-huh.
and then you're just trying to figure out, okay,
But yeah,
how are you supposed to know that it's CL3?
because the electron configuration tells you that it is going to have a +3. It's going to want 3 more electrons, essentially. Or so, yeah. And so this, and how would it bind with chlorine? Chlorine is over here, right? It wants 1 more electron. And so the way that they would bind together is you'd get 1 of these and 3 of these. Does that make sense?
Wouldn't it be the opposite?
No, because this is going to be sharing 3 electrons, 1 with each of the 3 other atoms. Does that make sense?
So the 3+ wants 3 more,
Yes.
and the 1- wants to get rid of 1.
No, it wants 1 more. They're not getting rid of, or they're sharing.
So what's the difference between 1+ and 1-?
1- is that let's see here, it gets 0 to 3. Oh wait, yeah, so it's sorry, it's trying to get rid of 3, but yeah, you're right.
That's what I was thinking.
Yeah. So it's this is giving up 3, trying to get 2. So remember that all ionic compounds are always trying to be like the noble gases, right? So aluminum tries to be a noble gas by going left, and chlorine tries to be a noble gas by going right. So 1s2, so it has 2 electrons. So look, 1s2 has 2 electrons in its first shell. 2s2, 2p2. So the p is here. 3s2 here, and then 3p1 puts us here. So 1, 2, 3. The p is over here. The s is over here. Really, you could put helium here. So 1s, 2s, 2p, 3s, 3p. Cool? Rock on. Okay, I'm going to assign a reading on that because I think that we need a review, and I'm going to find the reading. In fact, it's all kind of here together in this reading that I'm going to assign anyway. Okay, so we're going to let Alice, finish this up for
For
us.
the second question, a student claims that a compound with sodium and fluorine and a compound with oxygen and fluorine will have the same formula. Do you agree? Explain why or why not. Like many of the questions that we've answered before, this question requires you to do two things. You need to state whether you agree or disagree, and then explain why you feel this way. So again, press stop, answer the question, and press play when you're ready to continue.
Okay. So I want you to, the four of you, figure this out. Okay? Ready to go.
The same chemical formula, or
Student claims that a compound with sodium and fluorine and a compound with sodium and oxygen will have the same formula. Do you agree? Explain why or why not. Same formula as in you'll have, so sodium and fluorine would be like NaF2, and sodium and oxygen would be SO2, right? That's what they mean by the same formula. The ratio between the two elements would be the same. So, do you agree? Explain why or why not. Ready to go. And Elijah and Jeanette, I want you two to work together. I'm going to mute you over on my side.
So sodium and fluorine, I'm confused actually, sorry.
I'm getting kicked out, so I don't know how well that's gonna work out.
So fluorine would be different from oxygen, but they're in the same column on the table, right?
What do we determine? Or I guess Elijah and Jeanette are still working on it.
Well, I think that the student would make a mistake because fluorine and oxygen are in the same column.
Fluorine and oxygen are in the same column, but what about sodium? Oh wait, sodium and sodium. That's the same thing. Okay, so what did we?
So hopefully you said that you disagree.
Well, that's not what I wanted to do. What did we decide as people in class?
No, because the document worried about different electrons in the black shell.
So you said no. Elijah and Jeanette.
We also say no.
You say no.
Yeah. I was determining why the student would make that mistake.
Oh, okay. So yes, I disagree. Sodium ion has a charge of +1 or 1 plus. Fluoride has a charge of 1 minus, and oxygen. Fluoride and oxide, that is the nomenclature for an ionic compound. You put an "ide" if it's an ionic compound. The formula when Na and F bond will be NaF, sodium and oxygen will be Na2O. Okay? Disodium oxide. Cool?
Crochet.
Yes, Jeanette.
I keep on getting kicked out of the call for some reason.
Yeah, I'm sorry. You will be able to go back and watch the whole thing on YouTube.
Okay, thanks.
Sorry about that. Probably, yeah, good old computer issues. Okay? Are we clear on all that?
Yeah.
So we only have 5 minutes left of class. I'm going to end the recording. So let's see here.